Okay, so I'm showing 3:15, so I think we're ready to get going again. Donald, are you ready to go? Um, like to introduce our next speaker. Well, actually, let me sure. Are you ready to go, Donald? Are you there?
Yes, yes. Can you hear me?
Great. I sure can. Yes, our next speaker is Donald Long. He's currently at the University of North Dakota, but is going to be transferring to Howard University starting this fall, studying atmospheric science and social science. So Donald, go ahead and take it away.
All right. Thank you, Todd, for the introduction. So this presentation is a comparative case studies of the Unified Forecast System medium range weather application on HPC on-premise and AWS cloud architectures. And I'd just like to thank the Weather Program Office and also the William and Lapenta internship for the amazing opportunity this summer. All right, and so first, a few acronyms before we get into the presentation. So the UFS MRW means the Unified Forecast System Medium Range Weather Application. HPC is High Performance Computing. FV3 is the Finite Volume Dynamical Core discretized on a cube sphere grid. And for our particular project, we looked at the C96 resolution, which means you have a 96 by 96 grid. Each square of the cube has a 96 by 96 grid with a grid spacing of 1 degree. S4 is the supercomputer system used as the experimental variable. Hera is the supercomputer system used as the control. AWS is the Amazon Web Services cloud computing environment, and then CCPP is the Common Core physics package. And so this presentation is going to focus primarily on 3 things: modeling supercomputers in the cloud. And so the UFS is poised to become the go-to source system for NOAA's model development, and we'll get into kind of some thoughts around that. The UFS is also capable of being run on a variety of hardware specifications, both on-premise and in the cloud. So both using the cloud and using actual hardware, supercomputing hardware. And the cloud architecture provides a promising means of making the UFS more accessible to everyone. And we'll get into a little bit more about what in particular that means as well. And so just a project overview. So some of the goals were to build and compile the UFS on the S4 supercomputer, build and compile the UFS on Amazon Web Services, generate some regression tests so we can get kind of a benchmark for how the UFS is going to perform on each of these 2 systems, S4 and AWS. And from there, analyze those regression tests and then explore incentives for graduate students to develop using AWS, but also look at and think about how other people in the model development community can get involved as well. And then so some of the accomplishments, so we're able to build and compile the UFS on the S4 system. We generated those regression test results using the Hera system, which is a very similar system to the S4. We created an AWS account, and so we were also able to gather some cloud specifications from the AWS and create a startup guide, as AWS is sort of a new budding platform to get model development done. And so just a quick start guide, really an in-house thing that future people can use to get an AWS instance going. And then we created a document with the regression test output statistics to be used for future UFS model development. And so what is the UFS? So the UFS is essentially the model that is aimed at replacing a lot of the current research models. So if you think of the WRF, if you think of some of the other kind of developmental models, this system is people are hoping that this will replace those things for model development and kind of start here in terms of developing in the future. And so the specific version that we looked at is a medium range weather application, which forecasts out to around about 2 weeks. But the big thing, as the first bullet point says, is that it's community-based. And so we want, within NOAA, we want everyone to be developing using the UFS. And so that's sort of the challenge here, is getting not only all of government using it, but getting the academia, everybody involved with developing using this application with the goal of ultimately improving our models for the future. And so getting into the S4 system, so it stands for the Satellite simulations and data assimilation studies computer. Essentially, it is a large supercomputer that is at the University of Wisconsin-Madison, and this system is funded by NOAA, NESDIS, and STAR. And then what is AWS? So Amazon Web Services, like a couple previous presentations have mentioned, it is the on-demand cloud computing platform run by Amazon. They are the market leader in terms of web or on cloud computing. It's the future, and it allows for a more seamless and efficient workflow. And basically, with AWS or cloud computing in general, you can outsource your computing needs to a company like Amazon, for example, and it then becomes kind of a pay for what you need kind of platform. And so, in terms of you can think about different applications in terms of schools and things like that who may not have access to supercomputing grants and things like that, who may not have access to NOAA grants and things like that for the supercomputers. AWS then could become a viable option for them. So that's the big kind of idea with AWS. And so what exactly do we do? So we were able to copy the UFS medium-range weather application onto the S4 system. We're also able to build and compile the UFS on S4. We referenced Hera, which is a sister system for, because the UFS had been run on that system before, we were able to kind of use that as a guide as we went along. And so we are performing the regression tests on that system, but they are so similar that the results can be used effectively for this project. And then we were able to analyze those regression test results from Hera, as well as some output from AWS. And so again, we used a C96 resolution, 24-hour forecast. And then just so everyone's clear on what the regression tests are, you have, outside of the statistics world, in the modeling world, you have regression tests, and these are essentially used to develop and enhance the model. And so when someone comes with a new innovation for the model, developers have to then run and pass these regression tests, which test backwards compatibility. So you make some new code, you have to make sure that the model ultimately, in order for that code to get implemented into the final version of the model, everything has to run within the set time parameters that the model has in order to make it operational. And so that's what the regression tests really allow developers to see how different parts of the model are, how long they're taking to run. And so the UFS system, again, like I said, is on GitHub. And so when you go, you see that there's a wiki section, and this is under development. There's still a lot of people engaged with getting things going there. When you copy it onto your working directory, so this is my working S4 working directory on the left. You can see a lot of the things there are likely familiar to most people here. And then over on the right is what it looks like on the GitHub side of things. And so you can see a lot of the familiar components there. And so a summary of the Hera regression tests. So again, these regression tests test backwards compatibility after innovations are made. With Hera's regression tests, it's specifically, with the UFS specific regression test, it is testing the physics package, essentially. So the FV3 CCPP, that's essentially the physics package portion of the UFS, and it's compared, the control run of the physics package is compared in multiple configurations with 50 other tests. So you have the control run, that's one test, and then it's compared to 50 other tests. And it compares the atmosphere, the FV3 atmosphere, physics, dynamics, all for the 24 hours using restart files for the baseline control run, control configuration. And so to complete all of the tests, it takes 6 hours, 55 minutes, and 7 seconds. And so just getting into an overview of what these tests look like. So the blue line, or the blue arrow, is the control run, and we can see the prescribed nodes and tasks per node and things like that over on the side. Essentially, the nodes are just ways that the individual processing units speak to each other, in a sense, in terms of the supercomputing, the supercomputer itself. And then so down at the bottom is the purple line, or the purple arrow, and this is one of the debug cases. This one actually took the longest to run, and so that's likely because it is a lot of different flags in terms of the the model development are being activated with that particular test. And then over on the right with the light blue arrow, that one required the most processing power. That one was because these are just kind of some generic things to point out. But you'll see that it has the C768 resolution, so a very high resolution there. So kind of just a few overview things to point out here. We'll look at more in depth the purple arrow next to that particular debug case since it did take the longest. And again, we can see the runtime here over on the left is the time in seconds. And so around around 1,200 seconds is what that particular run took. And so again, with the blue arrow, you can see that that's how long the control run took. And so the standard deviation of all of these different tests in terms of their runtime is around 200 seconds. And just to point out again that the debug test is as long as it is, the red circle is as long as it is, because multiple debug diagnostic flags are turned on. So it's testing a lot of different things in terms of that. And so looking at kind of a breakdown of the control run in terms of the components, and so we can see the breakdown of the FV3 die core, the FV die core. And the point with all of these slides in this section is that these things will be extremely useful to model developers having to test different parts of their code. Again, so if you implement a piece of code into the model, you have to test it. And so if something, for example, is taking longer than it should, you can get pretty easily do a breakdown like this and kind of see where things are at. So if we take a look at the control run, which took at the top, you see 40 seconds to run total runtime. We compare that then to the debug test, and this one took, again, around 1,100 seconds to run. And so we could see kind of the breakdown here of the different components, and these different components are going to change depending on, how long it takes to run the model, how long, depending on what code structure you have and things like that. And so again, this is really for model developers that can get graphics and things that look like this, and they can also use the model output itself.
2 minutes, Donald.
Regression test outputs to take a look at these things. And so these are just a few of the kind of different, so looking at from a particular component, looking at the kind of output that you get. This is just kind of an overview of that, looking at how long different things take, how long each of the different tests took on an individual component. And so again, that's really for the developers. And so this is an overview of AWS. And so starting up an instance, you really just want to make sure the settings are all kind of geared towards what's given to you in terms of the group that you'll be working with. So that's kind of an overview of this. And then basically the run and cost statistics. So essentially from this, developers can estimate their costs with AWS. And then current estimates indicate that about 1 year total cost of storage and computing for a C96 run will cost around $10,000. Again, this presentation isn't to make exact judgments in terms of figures, but more generally, this is kind of an idea for runs and resolutions and things like that. And so a few lessons learned from this project. So cloud computing may be a viable option for schools with limited HPC budgets. The idea of UFS is to get the community involved. That means everybody from, high school students, potentially middle school students, all the way up to the professionals in NOAA, academia, all over. The UFS is easy to use, very versatile, user-friendly. It's going to take a lot of collaboration between NOAA and subject matter experts, and that's going to be key for research to operations and operations to research. And then personally, my interaction with the EPIC team has been very thoughtful and engaging throughout this process. And so in summary, the UFS is going to be the go-to system. That's the goal, very soon. And the cloud itself offers a promising means of making the UFS accessible to everyone. So again, thank you to the different entities that helped out during this project. It was greatly needed. And with that, I'll take any questions.
Great, thanks for that, Donald. We've got about 30 seconds for a quick question or two, if somebody can get something in quick. And looks like, Donald, how easy or difficult is now for you to run the model from your home institution if you were to do that? Does the cloud help you?
Yes, the cloud definitely helps, but the big thing with the cloud is just making, if you don't have access to a supercomputer, you can use the cloud. Or you can try it on, local systems and things like that, but it's still, depending on what you're doing, might be a little bit too much for a laptop, for example, or, other types of computing. But AWS provides a good, solid, strong computing setup for limited funds available for super.
Great, thanks a lot, Donald. So we'll need to move on. So thanks for that. If you want to stop sharing your screen, we can get ready for Leah. And so while she's getting that ready, our next speaker is Leah Hobson, and she's a bachelor's student in atmospheric and oceanic sciences at